Okay, so we just learned that the atomic number is equal to the number of protons, and that is what defines an element. But as we said in that video, that elements or atoms of an element can have different number of neutrons, and that is what leads to isotopes. Isotopes are atoms of an element with different number of neutrons and therefore different masses. So in this carbon sample that I just previously drew, all of the elements, all carbon atoms have 6 protons. That is what defines the carbon atom. Most of the carbon atoms also have 6 neutrons. A few, about 1% of carbon atoms have 7 neutrons. And a very, very small percentage of those atoms have 8 neutrons. I use few in the relative sense because in that carbon sample there's lots and lots and lots of atoms. So maybe I should change that, a small percentage. Small percentage of carbon atoms have 8 neutrons. Okay, and so that is what leads to isotopes. The percentages, the natural abundance of each of these isotopes is dependent on the nucleus stability. But another thing that we're going to use to differentiate between the isotopes is what's known as the mass number. The mass number of an atom is equal to the sum of the protons and neutrons. So the sum of the protons and neutrons. So for instance, the mass number of most of those carbon atoms with 6 protons and 6 neutrons is 12. And how we can write the mass number is we usually use a dash after the element's name and then the mass number, carbon 12. That's how we would refer to the isotope with 6 protons and 6 neutrons. We can also use just the element symbol, carb C12. About 1% of those isotopes with 7 neutrons, that would have a mass number of 13, of course. So we could talk about those isotopes, and we would refer to them as carbon-13 atoms, or C13 atoms. And of course, the very small percentage of those carbon atoms with 8 neutrons have a mass number of 8 plus 6, or 14. So carbon-14 is also in that carbon sample, or C14. And that's the isotope because it's radioactive that's actually used for carbon dating of historical or archaeological samples. You often hear the term carbon-14 dating. All right, so now that we know about isotopes, another thing that is important for every element is the atomic mass. Since each atom of those different isotopes have masses, what we're going to want to do is come up with an average mass for a carbon sample or any other elemental sample, and that of course is what we refer to as the atomic mass. The atomic mass is the average mass of an element taking into account the natural abundance of its isotopes, and of course their masses. Okay, so there's a very simple way to calculate the atomic mass of an element. What we do is we are going to sum all of the masses of each isotope multiplied by its fractional abundance in nature. So the one way we can write sum is using the Greek letter sigma, and all that means is summation, or sum up all of the atomic masses of each individual isotope multiplied by its fractional abundance. Now I mentioned I want to emphasize the fractional portion of this equation because it's usually reported, the natural abundances of isotopes are usually reported to in percent. Okay, so we're going to sum up the atomic mass times the fractional abundance. We're going to do this calculation and then add it to the same calculation for each isotope. Okay, so let's take a look at an example and we'll try to make sense of that equation. Okay, so here's a problem that we might want to solve. What's the atomic mass of chlorine, an element with the elemental symbol of Cl? Okay, chlorine has two naturally occurring isotopes, chlorine 35 and chlorine 37. Since chlorine has 17 protons, we can figure out how many neutrons each isotope has. Okay, so chlorine has 17 protons, and so chlorine 35 has 17 protons, and if we want to figure out how many neutrons it has, we just subtract 35 minus 17, and that comes out to 18. So that means chlorine 37 also has 17 protons. Every single chlorine atom has 17 protons. And then, of course, 37 minus 17 is 20. All right, so the atomic mass, the actual mass of chlorine 35 is 34.97 AMUs, and it has a percent natural abundance of 75.76. The other isotope, chlorine 37, has an exact mass, or atomic mass, of 36.96, and a natural abundance of 24.24. So let's calculate the average mass of these, taking into account the isotopic abundance, which of course is the atomic mass. So what we're going to do is we're going to take the atomic mass of chlorine 35 times its fractional abundance. We're going to add that to the atomic mass of chlorine 37 times its fractional abundance. And that's what we mean by sum up all of the isotopes. If chlorine had another isotope, natural occurring isotopes, we would do the same thing, same calculation for the third isotope and fourth if need be. But since it only has two, we can start this problem. Okay, so we're going to take the atomic mass of chlorine 35, which is 34.97 AMUs. We multiply that by the fractional abundance. The problem gave us the percent abundance, as it usually does. If you look up any isotopic abundances, it's usually reported to in percentage. But we want to multiply it by its percent abundance. So all we have to do is divide that value by 100 to get its fractional abundance. So 75.76 divided by 100 is 75.76. And we're going to add that to the atomic mass of the other isotope, chlorine-37, which is 36.96 AMUs, multiplied by its fractional abundance. Percent abundance is 24.24, so that means its fractional abundance, when I divide that by 100, is 0.2424. Okay, so let's start doing this problem. Got our calculator, got some a little bit of glare on it, but hopefully this will come out in the video. So the first value I'm going to do first, 34.97 times 0.7576. That's going to give me an atomic mass of 26.493272. And of course we have to think about significant figures. Since this is multiplication and division, we're going to use the least number of significant figures from our calculation. And so each value has 4, so we need to report this to 4. So this is 26.49 AMUs plus this value. So 36.96 times 0.2424 will give us a mass of 8.959104. And of course we need to cut that down to 4 significant figures as well. So that's going to be 8.959 AMUs. And then finally we've got to add these two values. 26.49 plus 8.959 gives us 35.449. But again, we've got to cut this down according to our significant figure rules. Since this is addition and subtraction, we've got to go with the least number of decimal places. I've got 2 and 3, so I've got to cut this down to 2. So that will give me a final answer of 35.45 atomic mass units, or AMUs.